Hello. So officially today is the first day of the summer 2 session. So let's start with the beginning. The topics we'll do today are the topics which are typically present in the first test, because they have 4 tests. So let me try to list a couple of them. We have to know the truth tables. We have to know to do inverse problems. Inverse problems. Then we have to be able to prove by contrapositive. I don't want to overdo it with proofs. Some important proofs, styles of proofs will do as proof by contrapositive or proofs by contradiction. And also, in the end, we want to do induction, mathematical induction. So let's do, that's the problem from each category. Right? So let's see. Truth tables. So let me select so for every compound proposition, we have a truth table. So for example, let's say the compound proposition is P and the negation of the proposition Q implies R. There's a compound proposition. So we want the truth table of this compound proposition. So let's try to build the truth table. So the first couple of columns are the atoms. So the columns of the atoms are P, Q, and R. Then at the head of the table, we gradually construct the compound proposition step by step, because every item at the head of the table follows from one item previously written or 2 items by applying a single logical connective. So what to do next? We already got Q and R, we can put Q implies R. Now, if we had Q implies R before, we can put a negation of Q implies R. So the negation of Q implies R. Now, we got P and non-Q implies R before, so we have the conjunction of P and non-Q implies R. So P and non-Q implies R. And this completes the truth table of this compound proposition. So, okay, so very important, again, the head of the truth table, we have the gradual construction of the compound proposition P and the negation of Q implies R. Again, another important thing, the number of lines in the truth table is 2 to the power the number of atoms. So we put here number of lines equals to 2 to the power the number of atoms. So in this case, it's 8. Right? Because we have 3 atoms, P, Q, R. So we have 8 lines in the truth table. So 1, 2, 3, 4, 5, 6, 7, and 8. 8 lines in the truth table, not including the header. This the header doesn't really count as a line on the truth table. Now, how to complete the columns of the atoms? These are the columns of the atoms. Columns of the atoms. There is a very, let's agree on a standard way of completing the columns of the atoms. So look at the column of the first atom. First half with T's, second half with F's. So true, 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 true. 4 T's and 4 F's. False, 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 false. For the next atom, repeat the same process but double the frequency. So instead of having 4 T's, 4 F's, we get 2 T's, 2 F's, 2 T's, 2 F's. So true, true, false, false, true, true, false, false. So we double the frequency from the first column. Double the frequency again. So instead of having true, true, false, false, true, true, false, false, we move quickly. True, false, true, false, true, false, true, false. Right. So true, false, true, false, true, false, true, false. By using this recipe, we just want to make sure that all the combination of truths and falses for the atoms PQR are taken into account. So true, 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 false, true, 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 false, true, true, false, false, and so on. All 8 combinations of true, false among the 3 atoms PQR are present here. Now, so that's pretty much automatic. So now let's complete the column after column. We have to complete each column by keeping in mind the meaning of the logical connective. P implies R. So the implication is very important. So most important to see when it is false. False never implies true, never implies false. So in other words, the most important thing about the implication, true never implies false. So let's see, when Q is true, R is false. Here. In the second line, Q is true, R is false, but then there's false. True never implies false. Because Q is true, R is false, Q implies R is false. True never implies false. Another possibility. Here, in the line number 1, 2, 3, 4, 5, 6, sixth line, true implies false is false. Because Q is true, R is false, Q implies R is false. Right? So 2 lines in which Q is true, R is false, Q implies R is false. The implication says if Q is true, then R is true. That's how to read alternative reading of the implication. If Q is true, then R is true. So if Q is true, R cannot be false. So truth leads only to truth. Truth never yields false. So that's why you put falses here when true implies false here and here. Right? Otherwise, it's true all the time. Okay, so that's the most sophisticated part in the truth table. Then the next one is easy. Negation just switches truths and falses, right? So it's all true, false, true, 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 false, true, true. Get true switches to false, false switches to true. So false, true, false, 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 true, false, false. This is the negation. The conjunction. I got the first column P conjunction with this one. The negation of P implies R. The conjunction of two proposition is true when both of them are true. So let's locate in those 2 columns when this and this are both true. Not here. Here is the case. Both of them are true. The conjunction is true if both of them are true. Let's see. Not the case. 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 So we have only one true in the final column of the truth table. Otherwise, we put else. And that's done. So that's the first problem. Could be a problem in the first test. You have to know how to build a truth table. So that's one important thing. Good. So let's move on to the next problem. So so far we went from the compound proposition to truth table. So the vice versa will be from truth table to compound proposition. But there is a catch here. From a truth table, we have to build a compound proposition which is in a particular form called disjunctive normal form. I'll explain to you in an example what does it mean. Okay, so now we are going through the inverse proof. So if we have the truth table, so we need a compound proposition. So let's see. Let's build a truth table. Just P, Q, and R. Let's say 3 atoms here. Okay, so 3 atoms, 8 lines. Because we have 3 atoms, number of lines is in a truth table is 2 to the power 3, which is 8 again. 1, 2, 3, 4, 5, 6, 7, and 8. Okay, so again, true. Let's pretty much automatic. 4 T's, 4 F's, false, double the frequency, true, false, true, false, then double the frequency again, true, false, true, false. Now, I want to put more problems for the price of 1 in a sense. So let's put phi 1. Phi 1 is a compound proposition which you have to find. So let's assume that phi 1 is a in the column of phi 1 we have a single T. So let's put here T here. And then F's. Let's try to think a little bit about what could phi 1 do. Okay, so look at this compound proposition. Phi 1 is true only in the first line. So in other words, phi 1 is true precisely when all of those atoms are true. So whenever P is true, Q is true, R is true, exactly in that place, phi 1 is true. So phi 1, by using this logic, phi 1 is P and Q and R. Because a conjunction of all 3 atoms, this conjunction of all 3 atoms is true precisely when all the atoms are true. So P and Q and R is true precisely when all 3 atoms P, Q, R are true, which is exactly what happens here. Phi1 is true precisely when P, Q, R are all true. So phi1 is P and Q and R. That's phi1. Okay, so let's try to put now phi2. It's a different problem. phi2. So let's try to go from the simple to complex. So let's assume that phi2 is still a single T, but in a different line. So let's put here in the 1, 2, 3, 4, the 5th line. A single T, but otherwise only F's. Okay, what will be phi2? phi2 again. So phi2 is true precisely when P is false, Q is true, R is true. So instead of saying P is false, Q is true. Okay. So it's only, so let's locate the T's here. So we have only one P in the column of phi2. So this single T happens precisely when P is false, Q is true, R is true. P is false, Q is true, R is true. But instead of saying P is false, Q is true, R is true, I'll just replace P is false with non-P true. Non-P is true instead of P false. So P is false is the same reading backwards. To read backwards P false is the same as reading and saying non-P is true. So phi2 is true, this compound proposition phi2 is true precisely when non-P is true, Q is true, R is true. So it's a conjunction of all those 3, non-P and Q and R. So non-P and Q and R. Okay, what's the rule of thumb how to build this proposition? It's a conjunction of the atoms or their negations. So a conjunction of terms, each term is a proposition which is either an atom P, Q, R, or a negation of that atoms of negation of P, non-P, or non-R. So that's a mean term, right? In a sense, we'll get better to discuss about this in Boolean algebra. So phi2 is non-P and Q and R. So how to do it completely and immediately? Look at the T in the column of phi2 and the true false assignments for PQR. False means the negation. T, leave the atom alone. T, leave the atom alone. So non-P and Q and R. It's exactly what we got here. phi3 is the most general problem of this type. we have a bunch of T's in all the columns, or all the rows. Right? Let's see, we got a T in the third row, a T in the fourth row, a T in the seventh row. We have three T's, and then only F's. So how do we phi3? For phi3, first of all, locate the T's in the column of phi3. So we have three T's, this one, and this one. For each T, write a conjunction of atoms / negation of the atoms. For this T, go along the line of this first T here. What we got here? P true, Q false, R true, right, for this T. So P, how do we read this? P unknown Q and R. P unknown Q and R. Because this P occurs when P is true, so P, Q is false or non Q, and R is true. So P unknown Q and R. Right? Or, so T is either in a row number 3 or row number 4 or row number 7. What's the connecting in those two phrases? Or, so P unknown Q and R, in a parenthesis, or what else? Look at the second T. This stands for what? P unknown Q unknown R. P unknown Q unknown R. Or, let me continue here. Or, 30. Let's follow the line of the 30. We get false, false, true. So non P and non Q and R. With the parenthesis, non P and non Q and R. There's a particular form for compound proposition which is called disjunctive normal form. Disjunctive normal form. Or D and F. Very important in logic. The disjunctive normal form. So now, this is a problem styles require. So asking, given a truth table, find a compound proposition in the disjunctive normal form, producing that truth table. So we did it by locating the T's column of the proposition. For every T, look at the line of that corresponding T, and look at the atoms. Whenever you see T, leave the atom alone. Whenever you see an F, negate the atom. So here for this one, the first T is P and non Q and R. The second T is P and non Q and non R. So or between them. The last T is non P and non Q and R, which is right here, non P and non Q and R. So that's important. That's the fastest explanation of the how to find a compound proposition in the disjunctive normal form, producing a given truth table. Okay, so now let's discuss about logically equivalent propositions. Essentially, logically equivalent is the same truth table. Logically equivalent propositions. So an example is, I don't know, let's see, P implies Q. This proposition, this compound proposition, equivalent non-Q implies non-Q. How to prove that two compound propositions are logically equivalent? Simply build a truth table for both of them. So look at the columns of the first column, the second, the two columns should be the same if they're in the same truth table. So let's build a truth table which contains the head of the table, the left-hand side and the right-hand side. So what are the atoms here? Only two atoms, P and Q. So we have 2 atoms to the power 2, which is 4 lines in the truth table. So that's simple truth table here. So P, Q are the atoms. Let's build the first proposition. P implies Q. You can build it immediately. P implies Q. Okay. To build the right-hand side, first we have to build non-Q. Then we'll build non-P. Then non-Q implies non-P. So basically, we got 2 for the price of 1. a single truth table in which two of the columns are one column is the left-hand side and the other column is the right-hand side. And in the end, we look at the two columns, we must conclude that they're identical for the two propositions to be logically equivalent. So two atoms, how many lines? 4 lines, right? Let's sort the truth table here. One, 2, 3, 4. Okay. Let's complete the columns of the atoms, like in a standardized way. First half with T's, true, true. Second half with F's, false, false. Then double the frequency, true, false, true, false. So we are done with atoms. We've got atoms. The atoms are P and Q. Now P implies Q. So like we discussed before, true only leads to truth. Truth never implies false. So what this happens? True, P is true, Q is false. So then P implies Q is false. Otherwise, true implies true is true. False implies true is true. False implies false is true. The only case we have a problem when true would imply false, which is false. Right? True leads only to truth. Truth can never yield false. Non-Q, flip the Q. So false, true, false, true. Non-P, flip the P. False, false, true, true. And then non-Q implies non-P. So let's locate when the quickest way to complete, locate the place when non-Q is true and non-P is false, because then the implication will be false. True never leads to false. So non-P is true. Non-Q is true and non-P is false. So true never yields false. So that's false. Because non-Q is true, non-P is false. Otherwise, this never happens that non-Q is true, non-P is false. Otherwise, non-Q implies non-P is true. Now, we have to prove that these two, the left-hand side is logically equivalent. These 3 lines here means logically equivalent. Look at the column of the left-hand side. Is this one. True, false, true, true. Look at the column of non-Q implies non-P. This is the column. And look at the two columns. If the two columns are equal, the equality of those two columns means the two compound propositions are logically equivalent. So that's one way to prove this stuff. The two compound propositions are logically equivalent. So this idea of the so-called proof by contradiction, just the easier form of the proof by contradiction, proof by contrapositive. So P implies Q means if P, whatever P means, then Q. Let me write it here. If P let's read again in plain language. This reads, if P, whatever P means, then Q, whatever Q means. That's the same as to say, if not Q, then non-P. So if Q is non-Q, if Q is false, then P is false. If Q is false, then P is false. So this idea behind proof by contrapositive. So if you want to prove a statement saying if P then Q, we just turn around and say if Q is false, then P is false. Let me give an example. So if P then Q is the same as say if non-Q then non-P. Example. Got a couple of examples for you here. Okay, so let's see. Let X be an integer. That's our first primitive proof. Prove that if x squared is odd, then x is odd. So let's try to use the idea of contrapositive to conclude this proof. So let x be an integer. Prove that if x squared is odd, then x is odd. That's our first proof. So that means x squared odd. Then so if then means implication. If x squared is odd, that means x is odd. There's an implication. P implies Q. There's P, our P, and our Q. What's contrapositive? Turn around. Instead of saying P, if P then Q, if non-Q, then non-P. If it is not the case that x is odd, then it's not the case that x squared is odd. So what does mean it's not the case that x is odd? What's the contrapositive? Contrapositive. If x is even, so there's non-Q. If x is even, then x squared is even. That's exactly the contrapositive. If P then Q, x squared odd, then x is odd. Turn things around. If x is even, then x squared is even. That's a contrapositive. How to prove that if x is even, then x squared is even, right? So let's try to write in a mathematical form that x is even. X is even number is twice some other number. So x equals to 2y for some integer y. Right? That means x is even. Right? So then, does it follow that x squared is even? What will be x squared then? So then, x squared, because x is 2y, x squared will be 2y quantity squared, which will be, if we square 2y, we get 4y squared, which is double some integer, so 2 times 2y squared. Because it's 2 times some integer, so that's integer. Because it's 2 times some integer, it's also even. So that's a conclusion of the proof by contrapositive. So because we show that if x is even, that means if x is 2y for some integer y, then x squared is 2 times 2y squared is also even. So if x is even, we show that x squared is also even. So this constitutes a proof by contrapositive. Okay. Let's do another one. Based on this, the whole idea, P implies Q, equivalent, non-Q implies non-P. Okay, so let x be a real number. Prove that if x squared is irrational, then x is irrational. So prove that if x squared is irrational, then x is irrational. So again, the idea is so in this case, we'll do more complicated proofs later, but today we want to restrict ourselves to contrapositive. So use contrapositive. There's a contrapositive. The logical base of proofs by contrapositive. P implies Q is the same with non-Q implies non-P. Use contrapositive. Okay, so let's see. Let's write the statement as an implication. So the implication is x squared is irrational. Implies if x squared is irrational, so x squared is irrational implies x is irrational. That's our P implies Q. And by using this logical equivalence, P implies Q is equivalent non-Q implies non-P. So this is what would be the contrapositive? It's a contrapositive reading of the same statement. Contrapositive reading of this implication. Contrapositive reading, right? If X, so look, the negation of the right implies the negation of the left. So the direct implication is left implies right. Contrapositive negation of the right implies negation of the left. So X is not irrational, so X is rational. Rational number means a quotient of two integers. Then X squared is rational. Again, so one more. So what does it mean rational? Rational means quotient of two integers. Of course, denominator is not zero. So like P over Q, P and Q are integers. P belongs to Z, Q belongs to Z, and Q is not zero. That's a rational number. A rational number is a quotient of two integers. Like 2 over 3 is rational. Or minus 11 over 19 is rational number. Quotient of two integers. So how to prove that if X is rational, so X squared irrational implies X is rational is the direct statement. The contrapositive is X rational, so negation of the right, X rational implies X squared is rational. Okay, so how to prove an implication? Suppose the left-hand side is true, then we do something, and then come out with right-hand side is also true. So what does it mean X is rational? That means X equals to P over Q. Like we wrote here, P over Q, P is integer, Q is integer, Q is non-zero. So then X squared equals to P over Q. How to square P over Q? P squared over Q squared. And again, it has the same form because we got P squared, P is an integer, Q is an integer, P squared is an integer, and here's integer, and non-zero, because Q is non-zero. So if X is P over Q, a quotient of two integers, then X squared, if we square a fraction P over Q, is P squared over Q squared. Again, a quotient of two integers. P squared is an integer, Q squared is an integer, non-zero. So that means X squared, we just proved that X squared is also a rational number because it's a quotient of two integers, and denominator is not zero. Okay, so let's try to so normally I wanted to do induction, but let's postpone a little bit induction so that just to reflect on the things we did today. So I'll see you tomorrow then, and we'll continue our discussion on logical themes. Okay.